Action potentials are the really fast electrical changes that happen across the membrane of certain cells, and often propagates from one cell to an adjacent cell, and cells in the heart communicate this way. Now, that signal's gotta start somewhere, so some of these cells, called pacemaker cells, have the responsibility of setting the rhythm and pace of the heartbeat. So they've got this really important job, but they're a relatively tiny group, and make up only about 1% of the heart cells. But they're able to continually generate new action potentials that get conducted to the rest of the heart, or the other 99%. And so these are what tell the heart to pump. The cells that receive that signal are called myocytes, because they make up the myocardium, which is the muscular middle layer of the heart. Myocytes are also called contractile cells, because they contract to allow the heart to pump blood. Myocytes are different from skeletal muscle cells, though, which get their action potential signals directly from neurons. Now, let's focus on a single myocyte cell going through a single action potential. The action potential of a myocyte is broken into 5 phases. Often they're shown on a graph of membrane potential versus time. We're going to start with phase 4, because why not? In phase 4, or the resting phase, our little myocyte friend is at rest, hanging out with an overall charge or membrane potential of negative 90 millivolts. Now, the interesting thing is that it has gap junctions, which are openings between two myocytes. So when the myocyte's neighbor depolarizes, some ions, mainly calcium ions, start leaking through the gap junctions, and that makes the membrane potential go up to about negative 70 millivolts. Negative 70 millivolts is called the threshold potential, and it marks the start of phase 0. Phase 0 is known as the depolarization phase. Basically, some voltage-gated sodium channels open up when they sense that the membrane potential is negative 70 millivolts, and they allow sodium to rush into the cell, creating an inward current. This rapid influx of sodium causes the myocyte's membrane potential to go all the way up to plus 20 millivolts. Now, if only a few ions had leaked through from the neighboring cell, and the membrane potential didn't get to the threshold potential of negative 70 millivolts, then those voltage-gated channels wouldn't open, and there'd be no depolarization. Essentially, there's nothing in between, which is why that we say an action potential is an all or none process. Alright, so if the membrane potential rises above negative 70 millivolts, and keeps going all the way to plus 20 millivolts, the myocyte is depolarized, and we're in phase 1, which is called initial repolarization. At this point, the sodium channels close and the voltage-gated potassium channels sense that it's at about plus 20 millivolts, and they open, allowing potassium ions to leave the cell. Those potassium ions have a positive charge, so the cell's membrane potential drops as this positive charge moves out. This is called an outward current, because it's literally a current moving out of the cell. So the membrane potential starts to fall, and we can see that this creates a little notch on our graph. Shortly after this, though, the voltage-gated calcium channels open up, and that allows calcium ions into the cell. As calcium flows in, it brings with it a positive charge. That positive charge from the calcium ions flowing in counterbalances the positive charge from the potassium ions that are flowing out. So the membrane potential actually stays pretty stable, and this is called phase 2, or the plateau phase. This calcium is super important because it's this influx of calcium that ultimately gets the myocyte to contract, which is how the heart contracts. So phase 2 is what's responsible for the length of the action potential as well as the heartbeat itself. During phase 3, or repolarization, the calcium channels close, but the potassium channels stay open, resulting in a net outward positive current. At the same time, ion pumps start to move calcium ions out of the cell as well, and that causes the heart to relax. Eventually, the membrane potential gets back to negative 90 millivolts, and we start over with phase 4 again. Alright, as a quick recap. Cardiac myocytes receive action potentials, or rapid voltage changes, from pacemaker cells. In phase 4, the myocytes are at rest. In phase 0, sodium channels open up and there's an influx of sodium ions that makes the myocyte depolarize. In phase 1, potassium channels open up, and there's an outflux of potassium ions that brings down the charge a little bit. In phase 2, calcium channels open up, and there's an influx of calcium ions, and that counterbalances the potassium ion outflux. So it's called the plateau phase. In phase 3, calcium channels close, but the potassium channels stay open. So there's an overall outflux of potassium ions that brings down the charge that repolarizes the myocyte. And then it enters the resting state again.